Good morning.
Good morning, Tim.
Good morning.
Good morning, Tim.
Good morning.
Good morning, Daniel. Okay, girls. Yes. Any questions now?
Yes. Can you go over the incident reflection and transmitted sound? It's on
Okay,
page
yeah.
92.
Okay, I don't need to make the paste. That's usual. Listen. What did we call an incident? Right, okay. Now we can mean it says, okay, no, since we are talking about sound, so we're just going to refer to as, okay, as the sound wave. Okay. That we can say, okay, it travels towards tissue, or which we also will call as, okay, a boundary. That is going to be known as a incident. Did that make sense? Right, okay, so we can mainly say as, okay, if we have a transducer, clear, we can just say, okay, yes, this is going to be as, okay, our tissue or our boundaries. Okay. Now, this transducer here is, okay, what is that going to do? That's going to just, okay, produce a sound wave that travels towards the tissue. So that is going to be referred to as an incident sound wave. Did that make sense?
Yes.
Good. Now what happens is, because, okay, you think that is okay, now what about the transmission? Clear? Now, once the sound wave, yes, okay, we can say, okay, hits a tissue boundary. Okay. Some of the energy is okay that the sound may have carried is going to be reflected back. Okay. Where we can say is, okay, the remaining energy is going to just, okay, carry on. And this will be as, okay, referred to as a transmission. So we can mainly say, okay, that based on that, we can mainly say, okay, that at transmission, we can say, okay, that's going to be as, okay, the sound wave that continues after it has hit, or we can say it's okay, from across a tissue boundary. Did that make sense? So the sound wave that continues after, yes, okay, the incident has hit a tissue boundary is going to be referred to as a transmission. But my dear, and that's probably okay where you got lost. This transmission here mainly is okay, is just going to as okay continue on to as okay the next tissue boundary, right? Right. So that's why it's okay. This also is okay become an incident. Right. Okay. It's going to be as okay a transmission of the wave that started as okay or before as okay hits this boundary. Okay. It's going to be a transmission, but mainly as okay because it's traveling towards a new tissue boundary. That's why it also becomes an incident.
Okay.
Did that make sense?
Yes, so,
Okay, just a second, my dear. And that's why I said, yes, okay, mainly as okay, just to understand the sets. We can say as okay, if this was as okay, your first tissue boundary, we can say as okay, second tissue boundary, third tissue boundary, fourth tissue boundary, fifth tissue boundary, sixth tissue boundary. We can mainly say that okay, as this here was the first incidence. Right, okay. Which then okay, as we'll have, yes, okay, the first transmission wave, which is mainly as okay, is going to also become okay as a second incident, which is going to have yes, okay, its own transmission wave, which is going to be a second transmission. Where this second transmission here is okay, just becomes the same as okay as a third incident. Did that make sense?
yes,
Right, okay. And what we mainly as okay can say is that okay, yes, we can say it's okay that the intensity of incidence 1 is going to be greater than the intensity of incidence 2. Or we could say yes, okay. Or in another way, yes, okay, or more or less we could say yes, okay, that the intensity of the incidence 1, right, okay, is going to be yes, okay, greater than okay as the intensity of the transmission 1. Okay, or greater, that is mainly as okay, just going to be as okay. The difference between these two, that is going to be as okay equal to as okay the intensity of the reflection. And what was reflection? Or reflected back. Likewise, okay, yes, where this second incidence here hits the second boundary. Okay, it may produce okay as a certain reflection. So the difference between yes, okay, the intensity of this incidence, which may as okay, just was okay as the first transmission. And yes, okay, the intensity of the reflection is going to be equal to yes, okay, the intensity of the transmission. But what we mainly as okay, see mainly because okay, greater or lesser amount of energy is okay carried by the incidence waves is going to get reflected. That's how it's okay. The intensity of the incidence is actually it's okay decreases as we proceed, and that decrease actually is okay what we call attenuation. Or have you guys, have you guys ever seen those rally races in the Olympics, where usually it's okay, the team has 4 members. Right, okay. But what is the whole thing? Is okay, whoever is okay, it's usually it's okay, just a roll of paper or whatever that they hold. Okay, but the main is okay, pass that on to the next person. Right, okay. Now, if you look at that, you can mainly say, okay, whoever is, for instance, okay, holding that, whatever they call that thing now, okay, it skipped my mind, in the hand, he or she is going to be as okay an example of an incidence. Okay, now it was the first runner who mainly as okay started the race, but what does it do? He or she is okay transferred over to the next. Okay, which for me is okay to be all okay as transmission. But now, yes, okay, this next runner, he or she is going to be as okay, just carrying that stick on to yes, okay, to the next runner. Okay, so although yes, okay, he or she received it from okay the previous runner, he is actually going to be a yes, okay transmission, but at the same time also an incident, because what is that he's going to do? Carry it on to the next athlete in the team. Did that make any sense? Okay. So yes, okay, what is a transmission? At the same time, yes, okay, will just become yes, okay, a new incidence. Why? Because okay, we said that okay, what was the incidence was? Any sound wave, yes, okay, that traveled towards a boundary. So as long as that sound wave is traveling and okay, that there's a tissue boundary ahead of it, it will be referred to as an incidence. Did you guys get that? Whereas, okay, as a transmission, that means, okay, there's going to be a sound wave that continues after a sound wave or an incident had hit or come across a boundary. So yes, okay, your transmission mean yes, okay, starts from here after the first boundary. But since yes, okay, this transmission mean yes, okay, just carries or yes, okay, it's a transmission of the first incidence, but since it continues on towards a second boundary or another boundary, it will also be referred to as a incidence. Clear? Although, yes, okay, this new incidence here is going to have an intensity that may be, and not maybe, most likely is lesser, yes, okay, than the initial intensity. Why? Because at the boundary, some of the energy that, okay, as this incidence here is, okay, carried was going to, yes, okay, get reflected back. So this becomes, yes, okay, a new intensity or a new incidence with a lower intensity than the first. How much low? Well, okay, that's going to be as okay when we subtract the intensity of the reflection from the initial intensity incidence. We will just okay get okay as the new intensity of this incidence, which actually is okay, as because it's okay. In this set here is okay, transmission. But that transmission just becomes a new incidence with a lower intensity. And the same, yes, okay, will happen at the second boundary, the same will happen at the third boundary, the same will happen at the fourth boundary, fifth boundary, sixth boundary, and so on. Okay, so we mainly as okay said about the intensities mainly was that okay, yes, the intensity of the incidence. Now, what was the incidence? We already said that any sound wave that travels towards the tissue boundary, that is actually yes, okay, going to be equal to yes, okay, the we can say yes, okay, intensity of reflection. What did we call a reflection? Mainly as okay, that sound wave that returned back or reflected back. Plus, yes, okay, the intensity of the transmission. Yeah, what was the transmission? Mainly as okay, that sound wave that is okay, because I continued in the same path as your incidence. This just becomes just okay, it's okay, reflection, or it's okay, a sound wave with a intensity that is lower than okay, yes, the intensity of the incidence. How low? All dependent upon okay, how much energy was reflected. But this does become yes, okay, we can say it's okay, this will just be yes, okay, a new incidence. Which means yes, okay, will have its yes, okay, well, the same amount of energy or same intensity as the difference of the first incidence and the reflection. But since it's okay, it's going to travel towards a new boundary, it's okay, that becomes it's okay, your next incidence. Right, okay. We could mainly as okay say the same about as okay what we call as okay intensity reflection coefficient. And or yes, okay, intensity transmission coefficient. That, but here is okay, the sum of these two here is mean yes, okay, that's going to be equal to yes, okay, the we can say okay, intensity of the incidence, which should make up a total of 100%. Because okay, these coefficients here mainly as okay was just a matter of how many percent of the incidence energy reflects back and become a reflection. How many percent of the intensity of the incidence does not reflect back, but actually is okay, continue on as a transmission. Did that make any sense? And Shaq, did I answer your question?
Yes, you did.
Okay. So you can mainly as okay, put it this way and say somebody is okay, get anything. You can take up anything. Okay, let's say something that we actually physically will be able to measure. Let's say it's okay, a box of donuts. Okay, that box of donuts may as okay be your incidence. Okay. Now, what is the command? The command or what's going to be as okay? The procedure that you made as okay will have to pass that box on. Now you receive it as the first one, so it's okay. What you received was okay as the incidence. You may take okay as a share of those donuts. What is going to happen? You pass it on to yes, okay, the next person. You passing it on is mainly as okay, going to be as okay, transmitting it on. Right, okay, so he or she is okay, receive yes, okay, the transmission from you. But what is it that he or she is going to do now? Mainly it's okay, just transfer it over. So that's okay, although yes, okay, he receives a transmission, but that transmission is also going to be as okay a new incidence because that person will have to pass that box of donuts on. He may say, well, okay, I already had breakfast. I'm not hungry. I don't want any donuts. Don't take any. Okay. So in that case, that's okay. What mainly will happen is that, okay, yes, the amount of donuts in the box, yes, okay, remains the same. You pass it on, that becomes, yes, okay. He transmits it. But that's going to be, yes, okay, become a new incidence because that next person also will have, yes, okay, transfer it on to the next person in the line. Did that make sense? Okay, so you only have a transmission once that's okay, an incident has hit a boundary. But that transmission made is okay, just becomes a new incidence because it's going to still travel on towards the next boundary. Okay, it will just have okay as a lesser amount of energy. Okay, how much less? Well, okay, primarily is okay. Not to go into all of the details, but as okay, mainly as okay, we just say depending upon okay how much energy was reflected back. Okay, and as the energy is okay transfers us okay moves from boundary to boundary to boundary to boundary, which means says okay moves deeper and deeper and deeper and deeper and deeper. What happens? The intensity of those sound waves yes okay will decrease, and that's what you call attenuation. Did you girls get that?
Yeah. I have a question.
Go ahead, my dear.
Can you explain one more time the conservation of energy, please?
Okay, listen, dear. Now, conservation of energy, yes, okay, we're going to, yes, okay, come across that law again and again, okay? Mainly, yes, okay, what it just says is, if you look at the word conservation of energy, but if you just look at the word conservation, yes, okay, it will pretty much, okay, let's explain itself. But we mainly can say, yes, okay, that energy can't be produced nor destroyed. Okay. Our main focus in this whole thing here is that that energy can't be destroyed. Okay. The next thing that we actually also will see is what can change its form. So let's just look at both of these parts here. Now, can't be destroyed. We already had that here. Because, okay, what was your intensity? What were your intensities? Just, okay, as a concentration of energy per area, right? Okay. Clear? So if you said that, okay, as we started off with, let's say, okay, yes, and our intensity of, let's say, yes, okay, 100 watts per centimeter square. Did that make sense? Right, okay.
Yeah.
And if we said that, okay, yes, now at a tissue boundary, yes, okay, the amount of energy that was reflected back. Well, let's say, yes, okay. Let's just say, yes, okay, that we had a reflection which was of an intensity which was 20 watts per centimeter square. Right, okay. That would mainly mean that, okay, as the intensity of our transmission is going to be as, okay, 80 watts per centimeter square. Clear? Why?
Yes.
Mainly as, okay, because when we add these two up, what do we get? 100 watts. Did that make sense?
Yeah.
Okay. It might, let's say, as, okay, if we, for instance, okay, had that, okay, as the intensity of our transmission would have been 70 watts per centimeter square. Though the reflection only was as, okay, still was 20. Well, okay, we will say, yes, okay, we are still missing
10.
10 watts per centimeter square. Okay, so that's mainly just, okay, where to say, okay, where did that go? Because it can't just disappear up in the blue here. Okay, so they may have said, okay, well, this is because, okay, as the might have been, as, okay, because there's, okay, some absorption. Okay, there might have been, yes, okay, some scattering. But right now, yes, okay, we mean, yes, okay, just talked about these two things here as, okay, as processes of attenuation. Or roughly what we mean is, okay, say, yes, okay, that. But even if he is, okay, took that into account, then because there's, okay, absorption, when it says, okay, was 10 watts per centimeter square. But when we still add it all up, we still, yes, okay, get 10 plus 70, which is 9, okay, which is 80, plus 20, which is 100.
Yes.
So we can say, yes, okay, all the energy that we started off with, yes, okay, we are going to be held accountable for it.
Okay.
Did that make sense?
Yeah.
So that's what we actually, yes, okay, meant by, yes, okay, that it can't get destroyed. By getting destroyed, we mainly mean, yes, okay, it's not going to be able to, yes, okay, disappear in the blue here. Right, okay. Clear?
Yes.
That's what you call, yes, okay, that's what you call accountability.
Mhm.
You can say, it's okay, each small little bit of energy is going to, yes, okay, be accounted for. You can't say, well, I don't know where the hell it went. Okay, no, there gotta be something that happened to that energy. Clear? Okay, so
Yeah.
you can't say, well, okay, yes, we started off with, okay, as 1,000 kilowatts. But as, okay, it just disappeared in the blue here. So it's okay, by the time it's okay, it reached its final destination, it's okay, we didn't have anything. What happened to it on the ways, we don't know. No, that gotta be somewhere. Clear? Okay,
Yeah.
so that was the first part of, okay, yes, your conservation of energy. Okay, clear?
Yes.
Now, whether you take that as, okay, yes, oh, what the hell? Now, whether you take that as, okay, as simple and said, well, okay, yes, 20 watts plus 80 watts, okay, yes, make up, yes, okay, what we started with. But we said, okay, yes, if you had 100%, because says, okay, we might have, okay, as 2% here, that will mainly mean that, okay, as this one here is going to be as, okay, 98%. Or yes, okay, what we started with, because these two percentages here have to be added up to make a total of 100%. Right, okay. Did that make sense?
Yes.
Good. Now the next part that we say is, okay, but energy is, okay, can change its form. And that's what we made as, okay, saw in chapter 8. Right, okay. Because what was it that we said in chapter 8? Well, okay, goes. The ultrasound machine is, okay, that runs on electricity. Or because that's, okay, electrical energy. Clear? Where this electrical energy came from? Well, okay, now there are different means, right? Okay. They may as, okay, make it out of oil. Or what you guys call gas. So more just, okay, electrical plants may be running on gas. And it just, okay, change that fuel energy into electrical energy. That's why, okay, a solar energy, for instance, okay, was also, what is that? Okay, that solar energy actually is, okay, is converted into electrical energy. So that conversion of just, okay, of one form into another form is, okay, as the second part of conservation of energy. Did that make sense?
Yes.
Likewise, if he says, okay, now this system is, okay, the system still runs on electrical energy. And we says, okay, it transmits electrical energy, yes, okay, to, yes, okay, this component here, which we call the transducer. Now, the main job of your transducer mainly, yes, okay, is or was, or is going to be, yes, okay, to transfer or change or convert this electrical energy here into sound energy. Where does this conversion from electrical energy to sound energy happen? That's going to happen during, yes, okay, what we call transmission. Now, when this sound energy here is, okay, comes back in form of, okay, as reflections of different surfaces, it is going to, yes, okay, be converted back into electrical energy. Okay, so yes, okay, the energy will mainly, yes, okay, just change its form. Okay, but the amount of energy is all going to, yes, okay, be accounted for. Did that make sense?
Yes.
So just because, yes, okay, a form of, yes, okay, or you can say, it's okay, energy, yes, okay, changes its form. But just, okay, the amount of energy that comes has to be, yes, okay, equal to the amount of energy that goes. That's what we call, as okay, being, as okay, energy efficient. Does that make sense?
Yes.
Okay. Any questions?
No, that's it. Thank you.
Okay, so when we add up, yes, okay, the different types of energies, you can say it's okay, reflection, that's a form of energy. If you look at it, transmission is just another form of energy. Okay, they're both going to be sounds, but yes, okay. Yeah. Anything else?
Not yet.
Not yet.
Page 104, question 3.
Page 104, question 3. Okay, dear. Let's see. So question 3 on page 104, right?
Yes.
Now let's see. Now sound pulse travels in medium 1 and strikes the interface or strikes an interface with another tissue. So we can mean it says, okay, that we have a medium 1. Okay. And we can say, okay, this one is okay. Now the interface, yes, okay, that's going to be, yes, okay, what we can call, yes, okay, the boundary. So that's what your book here is, okay, or question here is, okay, this refers to as an interface. Okay, so a sound, yes, okay, travels in medium 1 and strikes an interface with another tissue, medium 2. So that's going to be, it's okay, 2 mediums. So we have medium 1, we have medium 2. At an angle of 30 degrees. Now this is mean that's okay, going to be the angle here. That makes sense.
Yes.
Now the angle of transmission is 10 degrees. Right, okay. In which medium does the sound travel slowest? Now goes, I gave you goes the cheat. And I said, medium with greater angle is going to be the medium with greater speed. And okay, as when we look at this question here, we can mainly say as okay, medium with a lower angle is going to be as okay, the medium with the lower speed. That's the cheat that you need to look for. So what they may is okay is asking about is okay, which medium, okay, so in which medium is the speed or is the sound, does the sound travel slowest? What do you mean by slowest? Lowest speed. So that would be medium 2. Did that make sense? Whereas, okay, had it been the same question, same everything, but just the last sentence has changed and they said, okay, which medium has the greatest, in which medium does the sound travel fastest? It would have been medium 1. Okay. Did that make sense?
Yes, I think I was just reading the question wrong and reading it
No.
at medium 2 was 30 degrees and medium 1
No,
was
no, no, no,
10.
no, no. Because listen, and that says, okay, that's why, okay, a lot of the questions just, okay, here are not very straightforward. They try, it's okay, they tend to just, okay, twist and turn it around a little bit. Okay, so sometimes that's okay, you may have to read it as okay twice or thrice to just, okay, get it. But if you look at it, it says, a pulse is traveling in medium 1 and strikes an interface with another tissue, medium 2. So what does that mean? That means it just says, okay, that okay, we have a sound that travels in medium 1. Okay, we have a sound that travels in medium 1. And it strikes the interface, which is made as, okay, just another name of boundary. Okay, yes, at with another tissue medium 2. So the main is, okay, just label just, okay, the other medium as medium 2. But this sound wave, yes, okay, hits this boundary here at a 30-degree angle. Did that make sense?
Yes.
But then they even go on and say, yes, okay, so you shouldn't have confused it, but the angle of transmission is 10 degrees. Now, what was the transmission mean? Yes, okay, as we said earlier, any yes, okay, sound wave that travels beyond or travels after hitting a tissue boundary, or what in this case is, okay, called interface. So the main is like I just said, okay, as this angle here is 10 degrees. Angle of your transmission is 10 degrees. And then comes the last part, okay, is in which medium does the sound travel or travel slowest. Is that clear?
Yes.
Okay, so for those kind of questions here, just remember this one here. That is okay, the medium in which is okay, the sound travels slowest is going to be the medium with a greater angle. The medium in which the speed or in which the sound travels slow is going to be okay, the medium with the lesser angle.
Okay, thank you.
Right, okay. Okay. Now just keep in mind, guys, that okay, here they were gentle enough and say, okay, the medium that they started with was medium 1. And the medium is okay into which the sound wave continues is medium 2. But there are some questions that's okay, either it's okay, the exercise of the chapter, or it's okay in the review questions, where this medium with the incident actually is going to be referred to as medium 2. And okay, as the medium with the transmission is going to be referred to as medium 1. So you all have to, okay, figure those things out as okay from the questions, or the wording of the questions, which is, yes, okay, not that simple. Is that clear?
Yes.
Now, girls, we can also, okay, since we are at it, we can say it's okay. Why is there a difference of angle? That difference of angle is mean is okay because we had refraction. That makes sense? And what caused refraction is okay. First of all, we says okay, or incidence is okay, there was oblique. The second is that okay, yes, we have that the speeds between yes, okay, the two medias are not the same. And that's why it's okay to end up saying yes, okay, in which medium does the speed, does the sound travel at a lower speed, or it could have been yes, okay, greater speed. Or okay, what were your two requirements of refraction? oblique incidence. And okay, yes, different speeds. That will lead to, yes, okay, a refraction. And what was a refraction? That, okay, yes, the transmitted wave didn't continue at an angle of 30 degrees. That would have been the case if, okay, the speed had been the same. Because, okay, we had an oblique incidence. So mainly that's okay that it changes from as okay at 30 degree to as okay at 10 degree. Mainly mean that also as okay, the sound wave refracted. Okay, as when it hits the boundary or the interface, that it actually is okay. As we said, it's okay, it would bend and not continue straight. So this bend here, that is what we call a refraction, which is with an RA and not an LE. Because then this here is okay, will be your reflection. And what was the requirement for reflection to occur? That we actually is okay, just have different impedances. That the impedance of this medium was different from the impedance of this medium here. That is going to lead to a refraction. At a tissue boundary. Okay. What was our rule of reflection? Okay, yes, you only have a reflection if there is a difference in the impedance between the two medias. Okay, but the second rule of reflection was that, okay, as if we have a reflection, angle of incidence is always going to be equal to angle of reflection. Did that make sense?
Yes.
Yes.
Now, girls, how many of you did the questions for chapter number 6? Better be honest now than, okay, tomorrow and it's too late.
I did some of them, not all of
You
them.
did some of them, okay.
I did not. I need to.
You did not.
I did the ones in the chapter, but I didn't do the one in the back of the book.
You didn't do the ones back. Okay, so you didn't do the review questions.
Oh, yeah, I didn't do a few
Yeah.
questions.
And honestly, looking at the one in the chapter,
Hmm.
the
Threw
review
you
about
off?
attenuation, right? Attenuation and reflection.
Yeah,
On 106, we already did it when we went through chapter 6. I'm still
Mhm.
finding it hard to find it. I still find it hard to understand the answers.
So
On
the questions
106.
on 106.
Yeah, we already did it, so I don't know if you want to go through it again, but,
Well, okay, isn't that what we call a review? I don't mind.
oh, okay.
Go, that's what this, and that's why I said, it's okay, today is okay. If there's still something that you don't understand or don't, it's okay, get, or it may just has evaporated off your, it's okay, cerebral cortex.
Right,
Just let me know.
okay.
Okay.
This, like, I'm gonna be honest, the questions, the whole question from 1 to 9, being
Hmm.
able to get the answers from the information it gives me, I can't answer the questions without looking to the answers on the right side.
No, well, okay, that's the wrong way of doing it.
Yeah,
Because tomorrow you're not going to have the answers. Okay. So that's okay. Let me just try to just okay reproduce this whole thing here. So we can say as okay, we have a transducer, we have okay as a okay. Yes, good morning, dear. Yes, Dr. Haley. You want to say something, dear? Okay. All the best, dear. Right, okay, so what do we see here? So, okay, what do they say here? So, okay, this is just okay, your incidence, and it means okay, just have an intensity of this much. So we can mean it says okay, that's going to be as okay, your incident intensity, right? Clear? Then we as okay, just go and say as okay, we have different medias. So let me just go. Okay, let me say this. Okay, we have okay as this purple media here, which is media 1. And what does it have? Yes, okay, it has okay as a 1.5 rails. Okay, it has a speed of 1,450 meters per second. And okay, as it has a decibel, it has a okay, 3.5, sorry. Intensity coefficient, attenuation coefficient of 3.5 decibels per centimeter. Then we can go on and say it's okay, medium 2. And okay, as in all this is okay, just look at this as well. So it's okay. We say it's okay, what do we have here? It's okay, we have a okay, so we can it's okay, just continue on just like this. So what do we have here? It's okay, medium 2. First is okay, that's a 0.5 rails. We have a speed of okay, it's 1,450 meters per second, or okay, as 3.5 decibels per centimeter. And we have medium 3. And okay, as it has the same. Okay, it has okay, as the speed here, which is 1.45 meters per second. And okay, as we have a 3.5 decibels per centimeter. So this is medium 3. And then we go on to just okay, the next one, which will be this one here. Because I know it's okay, we don't have a purple or orange or whatever, but it's again, it's okay, 1.5 rails. Now this is 1,540 meters per second. And okay, as we still have okay as an incidence of yes, okay, incident coefficient of 3.5 decibels per centimeter. So this is just okay, your medium. Or yeah, now what is the first question that they are asking about? The first question that they say is okay, what does the 100 okay now milliwatts, okay, milliwatts per centimeter square represent? Now that's going to be as okay, your intensity of the incident. Did that make sense?
Yes.
Now what they mainly say is okay here is okay is what does this part 3.5, 3.5, 3.5, 3.5 represents? Well, okay, that should be obvious from yes, okay, from the unit. Decibels per centimeter, decibels per centimeter. So that's going to be as okay, your attenuation coefficient. Okay, and what we said is okay in the chapter as okay, what we said was that okay, once that was for instance okay calculated, it remains constant. Did that make sense?
Yes.
Okay, it should be obvious from the unit because okay, what the unit decibel per centimeter was, that was the unit for your attenuation coefficient. The amount of attenuation or decrease in power, intensity, and amplitude of the sound wave per centimeter. Did that make sense?
Yes.
Yeah. Now, question number 3. Now, if the media are soft tissue, let's say that all these media here is okay, was some sort of soft tissue. That's why they say if. What is an estimate of the ultrasound frequency? Right, okay. Now we already, yes, okay, if you remember, yes, okay, there was an equation. That means it says, okay, the frequency is okay, that was just going to be your attenuation coefficient divided by 2. Oh, sorry, that was you. Oh, sorry. What the hell? Sorry, that was not it. So that was the attenuation coefficient was, okay, sorry. Where were we? Okay. You could say it's okay that your attenuation coefficient. Okay, yes, that was what we said. So it was going to be, it's okay, the frequency divided by 2. But the maze is okay here. If this is okay, how will we calculate the frequency from your attenuation coefficient? That's just going to be, it's okay, the attenuation coefficient multiplied by 2. How do you get that? Mainly, it's okay, from this equation here, you said you multiply both sides by 2. So yes, okay, we can say this 2 cuts this, and you may say, okay, that your frequency then becomes twice your attenuation coefficient, which in this case is it was 3.5, and you multiply that by 2, it becomes 7. So we can say, okay, it'll be 7 megahertz. Clear? But just remember, yes, okay, that equation. Yeah. But from there, yes, okay, we can also say, yes, okay, if you double the attenuation coefficient, that becomes your frequency. Whereas on the other side, we can say, okay, that will be as okay, the attenuation coefficient, which says, okay, that will be as okay if you divide your frequency by 2, which here was 7. And when if you divide that by 2, it's okay, you get 3.5. So that will be as okay, your attenuation coefficient, which is going to be as okay. The unit for that was going to be decibels per centimeter. Okay, where did we get that from? Mainly, yes, okay, from this basic equation here. Did that make sense?
Yeah.
Good. What property has the unit of rails? How is that determined? So the mean is okay, just asking us, okay, this thing that we have marked here, yes, okay, the rails. What does that represent? That mean is okay, just represents, yes, okay, what we call the impedance. So rails was nothing that was mean is okay, just the unit of impedance. Clear? And what was determining as okay impedance? Or how do we calculate that? That would mean it's okay, just because it's okay, speed of sound times density. Right, okay, where is that given? Oh, yes, okay, in that short, yes, okay, section about impedance. Okay, which is not really much detailed, if you want to say it that way. But you find that on page 88 in your book. Yeah. Now, yes, okay, we can mean it's okay. Actually, it's okay looking at this diagram here. Because right now, it's okay, what is that they mean? Yes, okay, talk about, okay. What does these fellows here is okay represent? What does this fellow here is okay represent? What does this number here is okay represent? And okay, based on okay, as our frequency, okay, attenuation coefficient is okay, what was our frequency of our transducer here? Clear? Now let's just okay, as look at questions and okay, as me talk about okay, what happens at okay, different interfaces. So question number 5. The incident between the sound wave and boundary between media 1 and 2 is normal. So what they mainly say here is that okay, yes, when we talk, oops, between us, okay. Now what this is, the incidence between the okay, the incidence between the sound wave and the boundary between media 1 and media 2 is normal. Well, that's a little weird way of, it's okay saying, mentioning. They came and we take Omena and made it simple and say, it's okay, that the incidence at the boundary between media 1 and media 2 is normal. Why is that normal? Mainly because we see that the incidence, yes, okay, makes a 90-degree angle at the boundary between media 1 and media 2. So mainly that's okay because this here is a 90-degree angle. That's why we say it's okay that we have a normal incidence.
How do we know that based on the graph or the,
My dear,
from
look
just
here.
looking at, from just looking at it, how will we know that?
My dear, this is a 90-degree angle.
Well, I see that you drew that, yeah, but I'm saying just looking at this without you
Look at
giving us that
look at it
information.
in your book, my dear. You say it's okay, this is your boundary.
Oh,
Where you
you're
it's
saying,
okay, here have medium 1, and here you have medium 2, right? Clear? And this is your incidence. So what does this angle here does? What does this angle become? That's a 90-degree angle, right?
now I get it. Okay, yes.
So
Okay.
since it is a 90-degree angle, that incidence that it makes a 90-degree angle with a boundary is what we refer to as a normal incidence. Because the normal incidence means, okay, means that there was a 90-degree angle between the incidence and the boundary. That 90-degree angle could also be referred to as a right angle. That 90-degree angle could also be referred to as, okay, as a perpendicular angle. That 90-degree angle could also be referred to as an orthogonal angle. Clear? So when that is the case, that's okay, it will be referred to as a normal incidence. Whereas if this angle here was anything but 90 degree, you still had an incidence. This line here is okay as it continues. It is still going to be as okay your incidence. Clear? But if that doesn't make a 90-degree angle, then that becomes just okay, what we can call is okay an oblique incidence.
So I have a question.
Yeah,
So is the angle between medium 1 and 3 is a right angle too? Based on looking at the book?
yes,
Okay, thank you.
that will also be a 90-degree angle.
And then 3 to 4 is an oblique, right?
It will be oblique, exactly.
Okay, great, thanks.
Okay, because then you can say, okay, this angle here is not 90. Why is that not all this? Okay, your incidence is continuing straight. But it's okay, the boundary doesn't go straight. It's rather slanted, right? So this one here is going to be as okay and oblique incidence. Okay. Now what happens at the boundary between the two media and y? Clear? Now girls, between media 1 and media 2. that's okay, you will have a reflection with an LE. Let me just resolve this. Okay, so actually, it's okay. What we will have here is going to be as okay a reflection. And what determines that we have a reflection? Mainly, as I just said earlier, the difference in the impedances will lead to a reflection with an LE. Why? Because of the difference in the impedances. Is that clear?
Yes,
The reason that there is no refraction first of all is that's okay because we have a 90-degree angle incidence, or we had a normal incidence. The second reason is that okay, so even yes, okay, even if we have had an oblique angle, but it's okay if you look at the speeds, 1,450 meters per second, 1,450 meters per second. So it's okay, it says that's okay that the speeds in the two medias are the same. We will not have a refraction. And that would have been inspired even if we had had an oblique incidence. But here's okay, neither of the requirements of a refraction is fulfilled. So that's why it's okay, we don't have a refraction, but we have a reflection. Why? Because of the difference in the impedances between the two medias. Did that make sense?
yes,
Now, when they go on to the next question, and the first, okay, so now it's okay, we're just going to talk about it's okay, media 2 and media 3. So we're done between, it's okay, we promise, okay, done with media 1 and media 2. Now we're just going to say, it's okay, what happens? Here. Or rather, it's okay, at the boundary between medium 1 and medium 2. Or 2 and 3, sorry. Yeah, so again, it's okay, starts off with the same and say, well, okay, the incidence between the sound wave and the boundary between medium 2 and 3 is normal. What would that mean? That okay, we can always, or we can see that okay, it makes okay as a 90-degree angle. Clear? Okay, now comes the question. What happens at the boundary between these two medias here? And why? Now, girls, in this case, yes, okay, there will be no reflection. And why is that? Because your impedances in medium 1, 2 is equal to, that's okay, the impedance is medium 3. Did that make sense?
yes,
So since they are not different impedances as we had here between 1 and 2, that's why it's okay, there will be no reflection, because what was it I said? That we needed for a reflection to happen. Okay. A reflection is going to, yes, okay, only happen if the impedances were different. Here you have the same impedances, 5 rails or 0.5 rails and 0.5 rails. So since that's okay, the impedances in the both of the medias here are the same. That's why it's okay. We will not have a reflection at this interface. Did that make sense?
Yes.
Good. Question number 7. Now, what type of incidence is there between medium 3 and 4? And I already answered that one, right? So you're looking, shit. So the thing that they're talking about here is, okay, yes, what is the angle of, yes, okay, your incidence between, yes, okay, medium 3 and 4. So what is this angle here? There is an oblique incidence. Why is it an oblique incidence? Because it's okay, the angle here is not equal to 90 degrees. So this is not going, so this incidence here, you can mean it says, okay, that in medium 3 is okay, we actually end up having, okay, as an oblique incidence. Did that make sense?
Yes.
What did it mean to be oblique? That, okay, yes, that your angle was not 90 degrees. Or you didn't have a normal incidence. No, they may just ask us, just, okay, what happens? Now we already has, okay, established that, okay, this angle here is, okay, is the incidence angle here is oblique. So we can actually say, okay, yes, that here we have an incidence which was oblique. But now what they may ask is, okay, what happens at the boundary between 3 and 4? And why? Now, a lot of things are going to happen. First, we will have a reflection. And when I say reflection, that is the LE one, which mainly means that, okay, some energy is going to, okay, get reflected. Why is that? Because of the impedances between us, okay, the two media is not be the same. Did that make sense?
Yes.
Good. The second thing, my dear girl, that we are going to have is a refraction. The RA1, right? And why is that? First of all, yes, okay, because we have the oblique incidence. Okay, then we said, okay, that this angle of the incidence, yes, okay, is not 90 degrees. The second is, yes, okay, if you look that, okay, yes, we also have different speeds. Here it's at 1,450 meters per second. Whereas in this medium here is okay, the sound is traveling at a speed of 1,540 meters per second. So yes, okay, the next thing is all going to be that, okay, yes, that the speeds in the two medias are not the same. So since yes, okay, please mind it, since both your requirements for refraction are fulfilled, that's why it's okay, the sound beam may even refract. Here. Is that clear?
Yes.
Good. Now, what they mainly say is, okay, what occurs as the ultrasound passes through all the media? This. Clear? Okay, what happens as the ultrasound passes through the medium? And what are the units for this process? Well, okay, except from this one here, but what we mainly see is, okay, that the intensity will decrease. So that decrease in, yes, okay, in this case, yes, okay, intensity. That was what we call attenuation. And what was the unit for attenuation? Decibels. Did that make sense?
Yes.
Any doubts?
No.
Okay.
Now, because you went through, I don't know why, but now I can actually look at it and see like the 90 degrees and the oblique and the differences in it. Because before it just,
Yeah.
I was just looking at the
This
numbers
is
and
a
didn't
90
even
degree.
realize.
Okay, my dear, that's, I don't know at what, but this is mainly, yes, okay. Better don't say anything about. If we say this is a line. This here. A 90 degree angle between, you can say it's okay, line A and line B. Even yes, okay, this one here is going to be as okay, 90 degree angle between line A and line B. Now we can say as okay, this is your line A. And let's just okay use it in a different color. We can say okay, this was your line B. Now we can mainly say okay, this angle here. Maybe we can say okay. Let's just say it's okay, 60 degree angle. So that's okay, this is an oblique angle. Likewise, okay, I see you in this angle here. Okay, that's going to be, it's okay, 120-degree angle. But this is still, yes, okay. Oblique. Yes, okay, yes. The thing is that, okay, yes, the sum of these two here. And okay, as the sum of these two here is going to be, it's okay, 180. So that's when you say it's okay, if you were moving in this direction and you make a 180, you'll be traveling this way now. What does it mean? Just okay, make a 180. You make a U-turn. So I did that was not real, that's not even physics, that just, well, okay. Basic geometry. So that's okay, if something goes like this is a 90-degree angle. If I tilt it like this, it's not 90 degrees angle more. Or like this, it's not going to be 90 degrees angle. That's fine, yeah. Any further doubts?
No.
Okay, goals. Just take a short, should we say, 15 minutes break. Maybe you can browse through it, okay, some of your topics, and if you have any questions, then yes, okay. I'll be more than willing to answer them for you. Okay, girls?
Okay.
Yes, girls. Any questions?
I have a question.
Go ahead, my dear.
Could you go over the equation in chapter 7 where it says PRF is equal to 77,000 centimeters per second over imaging depth?
Okay. Okay, girls, now, as I said back then, and I mean, it's okay, it's just going to say the same now. Yeah, first of all, it's okay. That's the main, it's okay. Just we can say it's okay. First of all, it's okay. We can say it's okay, relating your PRF with imaging depth. Now, mainly as you see here, I said the PRF is equal to, yes, okay, some, yes, okay, constant figure in this case here. By imaging depth. What does that establish? That means it establishes, okay, as one fact, which is that PRF is inversely proportional to the imaging depth. Right, which may mean that, okay, as if we had a great imaging depth, we can say, okay, the VSOP scan to a depth of, let's say, 10 centimeters. We will have a low PRF. And or vice versa. If we phrase this, okay, scan to a shallower depth, let's just say it's okay, 5 centimeters. Right, okay. We will have a greater PRF. But what we mainly as okay, just will be doing in this, using this equation here, said, okay, if we need to, yes, okay, calculate the PRF. Now, what was the PRF? That was mean, yes, okay, there's going to be how many pulses do we have in a second? Right, okay. Now, your question may come in, okay, says, okay, where does this 77,000 come from? Because, okay, that was mean, it's okay, what we just say is, okay, was going to be, it's okay, a constant factor or number is okay in our equation here. I mean, it's okay, just divide that by our, it's okay, what we already said was, okay, yes, the imaging depth. Now here is okay, since that's okay, the beginning of this chapter is okay, we had mainly said, okay, as our imaging depth, that's going to be, okay, expressed in centimeters. Clear? Okay. Now this value here, 77,000, actually is okay, was derived from, is okay, your speed of sound in soft tissues divided by 2. Now this all, yes, okay, was okay, if we said that, okay, it was meters per second as the speed. So we mainly will say, I mean, yes, okay, just convert this meter here is okay into centimeters because the unit that we have here is also centimeters. So that could actually be the same as saying as okay that we have 15,000 is okay 150,000 4,000 centimeters per second. And why do we take second as a unit here? Because that's going to be as okay or unit for frequency, which means okay will just become yes okay hertz. Now when we say it's okay 154,000 divided by 2 becomes 77,000. So that's pretty much okay as where that value is derived from. Okay. And that's mainly because, okay, we mainly is okay, just use soft tissue as okay as a standard tissue. So yes, okay, pretty much okay, establish most of our equations in yes, okay, ultrasound.
So it's 77,000 divided by the image depth.
Exactly. But please keep in mind that okay, if your image depth has to be yes, okay, in centimeters. Right, okay. Okay. Because okay, if I said that your imaging depth was, oh yes, okay, let's say it's okay. I give you a question where I say it's okay, that your imaging depth, for instance, okay, was 1,000 millimeters. Oh, that's probably going to be a little too much. Let's say it's okay, 100 millimeters. You okay. If you divide, yes, okay, 77,000 by 100, you're going to just okay get okay as a very, very low PRF, which is actually that's okay going to be false. So first, what you will have to do is convert this here into centimeters. I mean, it's okay because as I said, just okay, millimeters. You mean as okay, well, you guys just okay divide the number of millimeters by 10, and that will give you as okay the number of centimeters that you had, which is just going to be 10 centimeters. Now you can take these 10 centimeters and say, okay, that is my imaging depth. That's how you, for instance, had here. Now, what is going to be my PRF? Oh, you can mean it's okay, just rewrite this whole thing. So that's okay, it's going to be 77,000 divided by the 10. Now, the easy way is that, okay, yes, that's okay, do that without, you can mean it's okay, this cuts this, and what are we left with? That's okay. 7,700. Now, please keep in mind, goal that this is going to be as okay hertz, not kilohertz, not megahertz, but hertz. Okay, but what does this is okay? 7,700 hertz means that if your imaging depth was 10 centimeters, you actually have okay, yes, 7,700 pulses per second. Each pulse is okay, will travel to a depth of okay as 10 centimeters and reflect back. And that's going to occur 7,700 times per second. Did that make sense? So that becomes just okay, your pulse repetition frequency. Okay. What is the frequency at which as okay, your pulse is being repeated in 1 second? Now, since we use the unit second here as okay, per second, that's going to be as okay, be hertz. But you can also say that okay, as this 7,700 hertz actually is going to be the same as saying 7.7 kilohertz. That's like saying yes, okay, 7,707 is going to be as okay, say that okay, as you will have 7. You can say okay, $1,000 bills, and then you will have okay, yes, that's okay, 7/10 of okay as $1,000 bill. Because okay, we expressed it as kilohertz. Did that make sense? So this number here is okay, 77,000 is mainly as okay, just derived from half of the speed of sound in soft tissues. Whereas the unit that we used for soft tissues was going to be as okay, centimeters per second. Why do we use centimeters? Mainly because, first of all, the depth is going to be expressed as centimeters. Clear? Okay, and based on that, yes, okay, the frequency that we get for the pulses is going to be as okay per second, which is going to be as okay hertz. So it's okay, if your depth was, let's say it's okay, 10 centimeters, that's okay, that is the PRF, or the frequency that you got. No, not frequency, sorry, PRF, sorry. Whereas, okay, now we can make it okay, let's say, okay, that if, let's just, okay, do it here, and okay, so it's okay, your PRF in hertz was going to be as okay, we said 77,000 divided by the depth, which was 10 centimeters. Right, becomes this much. 770 hertz. So we can make this okay, mainly because okay, we can say it's okay. In this case here, we had a great depth. Okay, we actually okay will have okay as a low ERF. Did that make sense? That was when we had okay as an imaging depth of 10 centimeters. Did that make sense? Where okay, the other example that we made is okay, just had here was okay as 5 centimeters. So you can mean yes, okay, do the same and say yes, okay, what would that be? So what would be the PRF in that case? Well, okay, you still have to yes, okay, this is just a constant number, 77,000. Okay, now you can mean this as okay, that B is okay divided by S okay, because it's okay a shallower depth, which we said okay is about 5 centimeter. Is going to be approximately as okay 15,400. Sorry. So that's okay. You said okay, it's 5 centimeters. Sorry. Okay. So what do we get here? We actually is okay have a PRF, which is going to be equal to is okay 15,400. What? Hertz. Very could say okay, that would just be equal to yes, okay, saying yes, okay, 15.4 kilohertz. Because it's okay, these 15,000 here actually is okay, became kilohertz, a whole kilohertz, where this means like recall it comes after the decimal. Yes, okay, and thousands is going to be yes, okay. Fractions of the kilohertz. Or we can make it as okay, this actually becomes 4/10 of a kilohertz. Right, okay. But you can still say that, okay, yes. 7,700 is a smaller number. Where, okay, 15,400 is a bigger number for your PRF. How did you get that? Because, okay, your imaging depth was shallower. Did you get that, my dear?
Yeah, I did.
Okay, okay. So that's okay. Unfortunately, it's okay. You just have to remember this 77,000 number here. Okay. But it is derived from the sound of speed and speed of sound in soft tissue. Clear? Okay. Which is mainly going to be as okay. Half of that sound speed in tissue, if that is expressed in using the unit centimeters per second.
I also have one other question.
Go ahead, my dear.
In chapter 8, when we talked about polarization and depolarization, could you like briefly go over that for me?
Listen, dear. When we said polarization, okay. Now, briefly, as okay, what we can call polarization as is, it means okay, there's going to be the process by which we can mean as okay, say as okay, one form of energy is converted into another. Right? Did that make sense? In our transducer, we could mean as okay, because it's okay, for instance, an example of that would be that electrical energy is converted into sound energy. Did that make sense? Did that make sense?
Yeah.
And the process that the sound wave is okay, that the energy undergoes to get converted from one form into another is what we call polarization. Where is this process here carried out? In the PCT. Did that make sense? So had we not had a PCT, yes, okay, your transducer was not going to be able to, yes, okay, in the first place, because it could convert electrical energy into sound energy. Or yes, okay, on the way back, convert that sound energy back into electrical energy. So that's all, yes, okay, when you can say it's okay, due to polarization, which is mean as okay, the process that enables one form of energy to be converted into another. Did that make sense?
Yeah.
Good. Now, ladies, when we say depolarization, now polarization, yes, okay, we already said what that was, right? What the prefix now, this here actually is okay, this DE here, that is actually is okay, a prefix. Is that clear? Okay, and what is that this prefix here is going to do? It actually is okay, going to is okay, cause, or the new word that we get is now depolarization. It's just going to be okay, become the opposite of, is okay, what we had here, the root word, which was polarization. Which mainly mean that okay, yes. Now, when we talk about depolarization here, what mainly mean that okay, whatever happened during polarization, but practically, yes, okay, either the opposite or in this case, yes, okay, we can mean it says okay that there will be no polarization. Did that make sense? So what would it mean that there will be no polarization? That okay, yes, that there will be no conversion of electrical energy into sound energy or vice versa. Why? Mainly because, okay, in this instance, yes, okay, because the component where, yes, okay, polarization was going to occur, which was your PZT active element crystal, has been damaged. So that would mean cause that, okay, the PCT, yes, okay, if that gets depolarized, that would mainly mean that it's not going to be able to polarize or, yes, okay, convert one form of energy into another, because it's not going to be able to, yes, okay, perform this process. Is that clear?
Yeah.
Okay. Now, girls, that was what we mean. Because it's okay, that polarization will mean, yes, okay, or polarization will mean in ultrasound physics. Okay. Those of you, and especially that's okay, those girls who are going to go for CBT. CBT, and especially that's okay when you, for instance, okay, study hard. Or it's okay, you echo and things like that. You will come across the terms again, polarization and depolarization of your cardiac muscles. Okay. And that, at that time, yes, okay, what is that polarization is going to mean? Well, strangely enough, okay, that your PC, no, sorry, your myocardium or your muscle is at a resting state. Or let's say it's okay, electrically not beating. Whereas depolarization is going to be as okay when your cardiac muscle becomes positively charged and actually it's okay goes into a contraction. But you can mainly say it's okay, either the muscle is resting, it is polarized, or it is okay going to contraction and become just okay depolarized, which is the opposite of being polarized. Did you girls get that? Okay, but here it's okay, polarization mainly mean that okay, yes, the process by which okay, yes, energy is converted from one form into another form. Where does that happen? In piezoelectrical materials. What did we call our piezoelectrical material of the transducer? We call that PZT. Where does PZT come from? Lead zirconate titanate. That was the name of the material that was used as a piezoelectrical material in the transducer. So ideally, yes, okay, it should be able to just okay polarize, which mainly mean able to yes, okay, carry out the process of carrying as okay, converting one form of energy into another. That process is what we call polarization. If it is not able to do so, that may mean that it is depolarized. Did that make sense?
Yeah.
Okay. What is going to be okay, a major factor of depolarization? Either yes, okay, physical damage. Okay. Somebody banged the patient with the transducer, that's okay. Drop it because that's okay. They call it crystal for a reason. It is going to be as okay, small pieces of crystal. Made up of what? Lead zirconate titanate. So yes, okay, it can get physically damaged by yes, okay. You guys says okay. Yes, okay, hitting it against yes, okay, hard surface. But okay, again, like okay, things such as okay, as exposing yes, okay, your transducer to yes, okay, super high temperatures beyond the Curie point or Curie temperature is also going to yes, okay, damage it. Now, what the hell was the Curie point or Curie temperature? That was the temperature that a piezoelectrical material reaches for it to be able to yes, okay, polarize. Right. So for different yes, okay, piezoelectrical materials, yes, okay, they have their own Curie points or Curie temperatures. Right, okay. What the Curie point or Curie temperature is for, let's say, yes, okay, your PZT or yes, okay, of your transducer, that's beyond the scope of this course. We're not going to go into all that. Clear? Okay. But it has, yes, okay, reached that temperature for it to be able to, yes, okay, polarize.
I have another question.
Yes, my dear, go ahead.
So for the non-imaging transducers, those
Yes,
ones, are they just the continuous wave transducer and the
Yeah.
therapeutic transducer?
listen, dear. Just look at it. And we said, okay, yes. We can mean say that, okay, yes, continuous wave transducer is also going to be known as non-imaging transducers, which is mean as okay, is going to be the same as what we can call as okay, therapeutic transducer. Clear? Now, why do we call it a continuous wave? Okay. Now, why wave? Mainly because okay, it is going to as okay produce waves. Why continuous? Mainly because okay, those waves are continuously being produced. So since they are continuously being produced, that will mainly mean that there is no off time. Or we can say, okay, there's going to be, okay, no listening time. Did that make sense?
Yeah.
Did that make sense, my dear? Okay. Now, we can mainly say, okay, now what happened in the off time? If we had a transducer with off time or listening time, that was mainly going to be that, okay, that transducer would have been a pulsed wave transducer, because it's going to be, okay, a short pulse, and then we had, okay, some sort of off time or listening time. And what was going to happen in this off time and listening time? That is actually, okay, the time that this pulse here will be given. That we give this pulse here a time to go to a certain depth and come back. And what is it that is going to bring back? Mainly, as okay, a reflection. So that's why it's okay, this pulsed wave transducer actually is okay, become what we call an imaging transducer. Because, okay, that's what we're going to is okay, use to is okay, get images. Since as okay, in a continuous wave, yes, okay, we don't have the off time. So we don't really give, yes, okay, these waves here, yes, okay, the time to, yes, okay, travel to a certain depth and come back. Well, okay, they will travel at just, okay, to whatever depths. But as okay, we are not going to be able to, yes, okay, get an image from it. So hence of that, that's okay, that's why they are referred to as non-imaging transducers. So they cannot be used to create an image. Did you get that, my dear?
Yeah, I did.
Good. Now, why do we call them as okay therapeutic transducers? Let's choose another color. Why do we call them therapeutic transducers? Now, just look at it. Well, okay, my dear, it is continuously non-stop producing some sort of wave in some sort of form of energy. We can say, it's okay, it may be sound energy, it may be vibrating, it may be whatever. That continuous energy, which is non-stop, actually is okay, is going to, is okay, we can say it's okay, being transmitted onto the tissues. Now, what's going to happen here, and that's the why they call it therapeutic, because therapeutic mainly comes from, it's okay, from therapy. What does therapy mean? Treatment. So it mainly is okay because it is continuously as okay transmitting energy. That energy as okay will most likely as okay get absorbed by the tissues. So you can actually see as okay, these transducers are continuous wave transducers as okay, may be used as massaging transducers. Okay. Or you may have as okay, those handheld massages. You say, okay, I have okay an aching shoulder. What is it that you do? You have those little small gadgets, and what does it do? Constantly as okay, transmit vibrations. Did that make sense? So what are those vibrations going to do? Those are going to okay, warm up your tissues and mean it's okay, going to okay, soothe it. Did that make sense? So mainly due to that, that's why they're called as okay, or just referred to as being therapeutic transducer, because well, okay, we may not get an image by using them, but they can actually, as okay, be used as you can say, okay, as source, yes, okay, warm up the tissues and okay, as okay, be a form of okay, as used as a form of treatment. Did that make sense?
Yeah.
Okay. So that's okay. The reason that we don't get an image is mainly because it's okay, there's no off time. So even if okay, as some reflections work to come back, that's okay. The domain that's okay, just be interfered by okay, that continuous transmitted wave.
I have a question about one of the equations in chapter 7.
Okay.
The one where it says depth equals 1.54 millimeters times go and return
Okay.
time.
Okay. Now listen dear. This is mean that's okay, just one equation that we may, yes, not necessarily as okay, may be using, but if you look at it, depth. Now it's okay for us here, it's okay, what's going to be the depth becoming it's okay, that will be it's okay, the distance. Because it's okay, traveled. To, let's say it's okay. Or we can do it this way and say it's okay. This here is our depth of the image. So we can mean this as okay. These 10 centimeters, what would that mean? That the sound travels at distance of 10 centimeters to get from point A to point B. Okay, so it can mean okay, that will be as okay, so it's okay, the distance. In this case, it's okay. That is okay, traveled from A to B, which we may as okay, just said was this distance here. Did that make sense? Then we again go on ladies, that's okay, and again that's okay as a fixed number. 1.54 millimeters per second. Now, where does that 1.54 millimeters come from? Or 1.54 millimeters per second? My idea, that's again, it's okay, that constant value of speed of sound in your soft tissues. Seconds, sorry, microseconds. Here. Did that make sense? Then here we said, now if you multiply that by as okay, where we just referred to in this chapter here as okay, as the go and return time. Now, as I said when I did this chapter back then, I said this go and return time here is mainly as okay, where we also could call time of flight. Right? Or we can actually say, okay, that is going to be as okay, your PRP. Both. And yes, okay, now the reason that we divided by 2 is because we made it okay, just looking at okay as the go time. Or we can say, okay, half of the total time of flight. Or half, or yes, okay, your PRP. To me, it's okay, said what will be the distance here if we travel at this constant speed. Right? Did that make sense? So it will mainly as okay, just be, just say as okay that you travel from, let's say as okay, point A to point B. Let's say as okay, your point A is, let's take any city here in Connecticut. Let's say it's okay, Milford. CT, right? Clear? To any as okay, any point B, we can say as okay, anywhere else, any other city. Let's say it's okay, Stanford. And we're talking of Stanford, Connecticut. Did that make sense? We made as okay, watch, yes, okay, say, well, okay, what was the distance between Milford and Connecticut? Did that make sense, my dear? Okay.
Yes.
Yeah.
So yes, okay, to determine this distance here. Biomay says, okay, well, my dear, we want you to, yes, okay, remain within the speed limits on the highway. So let's just say that, okay, as you go at a speed of, let's say, 60 miles per hour. Right? Did that make sense? Now it may take you, let's say, as okay, two hours. Now please keep in mind as okay to go from Milford to Stanford and come back. Because that becomes just okay, your go and return time. Did you get that, my dear? Okay, but what we mainly as okay, just wanted to know, yes, okay, what was the distance between, yes, okay, Stanford and Connecticut? So that's why it's okay, we divide this whole thing here, it's okay, by 2. That is straightforward because you can mean it says, okay, you travel at a speed of 60 miles per hour. It took you 2 hours to just, okay, go from Milford to Stanford and come back. Okay, so roughly speaking, yes, okay, you can mainly say, yes, okay. What we get here was going to be, yes, okay, we can say, it's okay. 120, that's okay, then just divide it by 2. Okay, if you want to put a unit to this, which is maybe going to be a little bit wild, but anyways, we can say it's okay. It's going to just okay be miles per hour multiplied by hour. Where you mean, yes, okay, mathematically you can say that, okay, yes, this hour cuts over this hour. And now you mean, yes, it's okay, yes. 120 miles divided by 2 will become the distance, which is going to be, yes, okay, 120 divided by 2 is going to be 60 miles. So that was the distance between Stanford and Connecticut. So mainly because, yes, okay, they use, yes, okay, the go and return time, which your book also, yes, okay, in this chapter I refer to as, okay, as your time of flight. Or which we mean, we could say, it's okay, that's going to be the pulse repetition period. Because it's only as okay when this pulse is okay, eventually as okay, return back. That, okay, yes, your second pulse will be sent out. So that's going to be, okay, a time period between the first pulse being sent out and the second pulse being sent out. That was what we call the pulse repetition period. Period at which, okay, as a pulse is going to be repeated. Did that make sense?
Yeah, thank you.
Okay. But just okay, the main thing goes as okay, as your 13 microsecond rule. That's the main thing. Okay. So you can say, okay, the equation of okay as your PRP, which means okay, that's going to be as okay the product of the imaging depth and 13 microseconds per centimeter. Is more important. Okay. Where you then mean you can say as okay, the imaging depth is just going to be as okay, your PRP divided by 13. What 13 microseconds. Any other questions?
I have one.
Yes, my head. Yeah, go ahead, please.
Can you go over where it says, it's like the beginning of chapter 6, where it says the final power is 1/10 of initial power and initial power is 10 times of final power?
Okay, my dear. Now, when it goes by tens, that is going to be as okay, what we can say as okay log. Because my dear is okay, what was your log? And we write, okay, something like, okay, as 10 raised to the power, let's say 2. Here's okay, this 2 here is your log. Or as okay, more accurately speaking, is okay, the logarithm. Here. Now, if we say that, okay, as the final power is 10 times 2, 10 raised to the power 2 of the initial power. Now mainly as okay mean that okay, yes, what is 10 times 2? What does this 10 raised to the power 2 actually means? It means 10 multiplied by 10, which means to me that okay, your final power is 100 times greater than the initial power. Did that make sense?
Yeah.
It's mainly just for me that, okay, yes, then your initial power is going to be equal to, yes, okay, 1 over 100 of the final power. And what is this 1 over 100 going to be? That's okay, that's just going to be written as 10 raised to the power minus 2. So here is okay, it actually becomes as okay, what we can say is okay, it actually becomes a negative log. What does the negative mean? That is less. Did that make sense?
Yeah.
Okay. Now this guy is okay, when we say like that the final power is going to be greater than the initial. That's something, this is mean it's okay, going to be something that we will come across in chapter 14. Which actually is going to be the opposite of your attenuation. Clear? Because in attenuation, we can mean it says, okay, if we said attenuation is okay, in that case, that's okay, the initial power that was greater, and okay, as your final power, that was going to be lower. Clear? So when we go with that, we can mean it's okay, say that, okay, then the final power is okay, maybe 10 raised to the power minus any number. If we said that is okay, says, let's say minus 4, that would mainly mean 10,000 of the initial power. Yeah, we then just for me that okay, as your initial power is 10,000 times greater than the final power. Did you get that?
Yeah, I got it.
Clear? Okay. So the logarithm masculine means okay, there's going to be okay that multiple of tens. Okay, but when your logarithm is negative, that will mainly mean that okay, as I think decreased. Or what you compare it to as okay is going to be lesser than the number that you're comparing it to. So that is okay, which is bigger, which is smaller, is okay, switches all dependent upon, it's okay, if you talk about attenuation, or it's okay, as we will talk about in chapter 14, amplification. Because in attenuation, yes, okay, your initial power is greater, final power is lesser. Why? Because the sound wave is okay, decreases in its power as it travels through the tissues. That decrease in the power was what we call attenuation. So you may have, okay, as a great initial power. After this, okay, it keeps on attenuating, it decreases to a lesser power. It doesn't really decrease, that's okay. Some of that energy that the power, that's okay, that the initial sound wave was carrying is reflected back. Some of it is scattered, some of it is absorbed by the tissues. Did that make sense? Did that make sense?
Yeah.
Okay. Whereas, okay, as you will see in chapter 14 is going to be the same. It's okay. What power is okay do we have in the beginning versus that's okay what's going to be the power at the end. But okay, there's going to be it's okay in a different direction and all that. So let's not get into that. But in that case, you can say it's okay, the initial power is going to be lesser than the final power. So that's when you say it's okay, that the gains. Gains how much? 10 times, 100 times, 1,000 times, 10,000 times, 100,000 times, a million times, trillion times, whatever. That's all going to be as okay, dependent upon as okay, your exponent of your logarithm. But if that exponent is okay, as indicated with a negative sign, it means that okay, yes, it is decreased. Whereas if there's no symbol, that will automatically mean that okay, yes, it is a positive logarithm value, which mainly will mean that okay, yes, it increased. How many times? That's okay. The times that you multiply 10 by itself. Because my idea, what we mainly said was, we can say it's okay, 10 raised to the power 2 actually is okay, means 10 multiplied by 10. And what do you get from that? You get 100, right? Right? We said 10 raised to the power 3. What would that mean? That mainly means 10 multiplied by 10 multiplied by 10. And what do you get from that? You get 1,000. You can go on and say, okay, 10 raised to the power 4. What does that mean? 10 multiplied by 10 multiplied by 10 multiplied by 10, which becomes 10,000. And so on. You can go, yes, okay, 10 raised to the power 5, which means it's going to mean the same. 5 times, which becomes, yes, okay, 100,000. You go, yes, okay, 10 raised to the power 6, that means, yes, okay, means 10 multiplied. 6, which becomes, yes, okay, million. And so on. Whereas, okay, if you go this. That means, okay, just mean 1 over 10 multiplied by 10, which means, okay, become 1 over 100. You go this, what does that mean? 1 multiplied by 10, or 1 over 10 multiplied by 10 multiplied by 10, which becomes 1 over 1,000. And so on. $10,000 or 10 multiplied by 10 multiplied by 10 multiplied by 10. Oh, yes, okay. 100,000 or 10 multiplied by 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 10. Oh, yes, okay. 1 over 1,000,000. Just because it's okay, it was a negative exponent. So what that negative mainly is, okay, means that it becomes just okay a fraction. Clear? And please keep in mind, go just okay, a fraction can also just okay be expressed as a decimal number. Did you guys get that?
I have a question.
Mhm.
It's not about the book. I just want, is the quiz gonna be more like direct? Because you know how like in the book, the wording of the questions is tricky.
I don't know. The wording of the book is tricky. Okay.
Because you know how like in some questions you
Yeah,
say like,
I know.
oh, okay.
But that's okay. How it's okay. You can say it's okay. He authored it, or he wrote it. I may as okay reproduce that question in another way, and may change the wording, and even that wording may be confusing.
Okay.
Okay. Because yes, okay, there is no golden standard way of okay, yes, formulating a question, if you want to put it that way. The main thing that you just need to is okay, look at okay as what do I get from yes, okay, what is that the question here states? What are going to be as okay the relevant information, and what maybe is okay irrelevant. Clear, all dependent upon is okay what the questions ask you about. Yes, okay, either calculate or determine or is okay. Yes, okay, specify the relationship or so and so about. I mean, it's okay, just okay, help you goes out. And that's why it's okay, I went over it's okay. The question and say, okay, listen. This is what it means, although yes, okay, it is in a little odd way of explaining, yes, okay, stating it. This could have been stated in another way. But okay, that's the way that the person here, Dr. Sidney K. Edelman, yes, okay, worded the questions. So anything else? Yes, girls. Anything else? Okay, good. Now you can take your lunch break. Yes, okay, you can come back, you can read, and if you still have any questions, I'd be around to answer them for you, okay? Does that sound like a deal? Or no deal?
Deal.
Deal, okay. Have fun, bon appetit.